Greetings, everyone. My name is Peter Oyok, and today we're discussing about the cache. This is a small section of a SRAM memory added between the main memory and the processor to speed up the process of execution, known as the cache memory. This measures effectively the cache fulfills the request of getting content. If data has been found in the cache, it is the cache hit else it missing. Let's talk about cache mapping. According to our slides, you see cache mapping mapping function, a certain main memory block can be mapped to a specific cache block using the mapping functions. The block is moved from the main memory to cache memory using this mapping function. And there are three available mapping functions. For example, let's talk about the direct mapping. Each block from the main memory has only one possible place in the cache organization with this technique. Next, we have direct mapping. Next, we have associate mapping. Any main memory block may potentially reside in any cache block position according to the map algorithm. The mapping methods offers a greater flexibility on all this. And also, here the mapping of the main memory block can be done with any of the cache block. Memory address has only two fields here, the word and the tag. This technique is called as fully associate cache mapping. We have examples on this shared in the Word document. Let's talk about the third one called block set associate mapping. Others let's call it the set associate mapping. It is a combination of advantageous both direct and associate mapping. Here the cache consists of a number of sets, each of which consists of a number of blocks. And this refers to as the Elway set associate mapping. To map the memory address to the cache, using the field in the memory address, we access the particular set of cache, then the tag bits in the address are compared with tag of all L blocks within the set. For a match, a cache hit occur as required what is found in the cache. Otherwise, the cache miss occurs and the required word has to be brought in the cache from the main memory. According to the replacement policy used, a replacement is done if the cache is full. A replacement algorithm, choosing which of the previous blocks to replace is necessary when a new block needs to be added to the cache, and every available space is taken. Generally speaking, when a block is expected to be referenced soon, a policy must be in place to keep it in cache. Finding out exactly which blocks in the cache are going to be difficult. So the locality, the reference property provides some guidance in designing an effective replacement policy. For example, the list recently used replacement policy. It is reasonably assumed that there is a high linkable on that blocks that have been prepared recently will also be referenced in the near future because programs typically remain in localized areas for reasonable periods of time. That makes sense to replace the block that hasn't been launched when the block needs to be overwritten. The least recently used block is what this is. It is necessary to monitor the block while the computation is running. First in, first out replacement policy. When a block needs to be brought in, it might be reasonable to remove all this from the entire set when hit happens while employing this method. No update is necessary when a miss happens and the set is not full. The encounter values of the specified block are increased by 1 and the new block is placed into an empty block. A means causes a set to fill, at which point the block with highest counter value is replaced with a new block and the counter is set to 0. The counter value of each additional block in the set is then increased by 1, since there is no requirement for updates during it. The overhead of the policy is reduced. The random replacement policy, selected block overwriting at random, simplest algorithm. Paradoxically, it has been discovered that this straightforward algorithm works incredibly well in real-world situations. There are times whereby one would ask, what are the differences in direct mapping, associative mapping, and set associative mapping? Let's just give a few examples. Just a few examples. For example, the direct mapping. The main memory address is divided into 3. Here. That's a tag, the block, and the word. The block and the word together make an index. The least significant word bits identify a unique word within a block of main memory. The block bits specify one of the blocks. The tag are the most significant bits. The next one is the associate mapping. The main memory address is divided into 1 as a tag and 1. Then the set associate, which is sometimes called the block set associate mapping. The main memory address is divided into 3. That's a tag, the set, and the word. Getting to the second difference between these, the index is given by the number of blocks in caching. That's direct mapping. The index is given by the number of blocks in caching. Associate mapping. The index is 0, associate mapping. Then for the set associate mapping, the index is given by the number of sets in caching. These are some of the few differences among these mappings. Lastly, or probably list, if the processor needs to access the same memory location from 2 different main memory pages frequently, cache hit ratio decreases. That is the direct mapping. Whereas associate mapping, if the memory needs to access the same memory location from 2 different main memory pages frequency, cache hit ratio has no effect. And for the set associate, in case of frequently accessing 2 different pages of the main memory, if reduced, cache hit ratio reduces. I guess I have this for my presentation today. Thank you very much.